In this section, we're going to take a look at the double angle, the half angle, and the power reduction formulas.
Recall the sum and difference formulas for the sine and the cosine function. The sine of a plus b is equal to the sine of a times the cosine of b plus the cosine of a times the sine of b. Like that. Okay. Also, the cosine of a plus b, that's equal to the cosine of a times the cosine of b minus the sine of a times the sine of b. Or whatever else you want to call your angles, alpha, beta, theta 1, theta 2, or any other designation you care to use, x and y for that matter. From these two, we can derive a few others that are equivalent to these, but useful to know in their own right. So first of all, let's say we actually had two of the same angle. So instead of sine of a plus b, let's say we had sine of a plus another a. So sine of a plus a. Okay, well that would be the same that we have here, except all of these b's would be replaced by a's. So that would be the sine of a times the cosine of, the b is replaced by an a, plus the cosine of a times the sine of, and again your b is replaced by an a. Well, notice those are the same thing. Cosine a, sine a, cosine a, sine a. They're in a different order, but multiplication is commutative. It doesn't matter what order they're written in, you have the same result. So here, this is equal to double this. Double sine of a cosine of a. This is called the double angle formula for the sine function. Here we have, and I'll go ahead and leave some space here so we can do cosine in just a moment. Here we have sine of double, and in most books, including ours, I believe, it says sine of 2 theta instead of sine of 2a. It doesn't really make any difference. Right? Sine of double of an angle is equal to double the sine of the original angle before you doubled it times the cosine of that same angle. And so here we just replace our a's with thetas. Sine of 2a, okay, sine of 2 theta, is equal to 2 sine of a cosine of a. Okay, 2 sine of theta cosine of theta. Likewise, we have the cosine of a plus a. Okay, well, in that case, same thing. We're replacing these b's with a's. So that'll be cosine of a times cosine of another a minus the sine of a times the sine of another a. Or in other words, cosine of a times cosine of a, that's cosine squared of a. Multiply something times itself is the same as squaring it, minus sine squared of a. This should remind you of the Pythagorean identity. Right? If you have cosine squared of a plus sine squared of a, that equals to 1. But instead of a plus, if you have a minus here, that's the double angle formula for the cosine function. The cosine of double an angle is equal to cosine squared of that angle minus sine squared of that angle. Now, there are other ways of writing this same result. For example, using the Pythagorean identity, I know sine squared of a plus cosine squared of a is equal to 1. So here, cosine squared of a can also be written as 1 minus sine squared of a. That's by the Pythagorean identity. So if this can be written this way, minus sine squared of a, well then these double up. So this would give us 1 minus double sine squared of a. So that's another version of the double angle formula for cosine. The double angle formula for sine, there's only one version of that, but the cosine has several double angle formulas, and they're all equivalent, but come in useful at different times. Likewise, if instead of taking this one and writing it in terms of sine, if we took this one and wrote it in terms of cosine, that would be cosine squared of a. That's going to stay the way it is. That one is that one. Right? This one became those two, or we can leave it that way. And now this one, before it stayed as it was, but now we can go ahead and change it into 1 minus the cosine of A, like this. So that one term becomes these two terms by the Pythagorean identity. Note that you can now combine like terms. Cosine squared of A minus a minus, so plus cosine squared of A. That's double cosine squared of A, minus 1. So that's another version of the double angle formula for the cosine function. Double the cosine squared of A minus 1 is, I guess I should write these all as thetas. Double the cosine squared of theta minus 1 is the same as 1 minus double the sine squared of theta is equal to cosine squared of theta minus sine squared of theta, because all of those are equal to cosine of double theta. Now for the tangent, we can either start with these and divide them into each other, taking sine of a plus b over cosine of a plus b to get tangent of a plus b, or we can remember what that was from before. Here the tangent of a plus b is equal to the tangent of a plus the tangent of b over 1 minus tangent of A times tangent of B. And it seems I've planned poorly. I didn't have enough space for that one. But here, 1 minus tangent of A times tangent of B, and then the numerator is tangent of A plus tangent of B. Okay? Well, if I replace both of these with the same expression, if I say, okay, that's the tangent of A plus A, well, again, these B's are going to become A's. So this would be tangent of A plus another tangent of A over 1 minus tangent of A times another tangent of A, which would be, well, that's double the tangent of A over 1 minus tangent of A times itself, well, that would be tangent squared of A. Okay? So that's double the angle in a tangent. So this would be the double angle formula for the tangent function here. That is tangent of double theta, tangent double the angle, is equal to double the tangent of the angle divided by 1 minus the square of the tangent of that angle. Here, these two are common. Using a double angle formula for sine and cosine appears in a lot of trigonometry and in a lot of problems in calculus. However, tangent is a lot less common, and if it does show up, you can always derive it using sine of 2 theta over cosine of 2 theta. Right? So these are the so-called double angle formulas. For obvious reasons, they take the sine of double of a normal angle. And the double angle formulas are useful and in fact are necessary because, well, the sine, the cosine, the tangent functions are not linear. With linear functions, if you say I'm taking double the input, well then I'll just have double the output. Right? Sine of 2 theta would be 2 sine of theta. But sine, cosine, and tangent are not linear, so they're not just, oh, if I'm doubling the input, I'll double the output. There is more to it than that. Right? So for example, let's say we had the following illustration. You have a triangle, it's a right triangle, and the sides of this triangle are 3, 4, and 5. Maybe I should say 3, 4, and 5 to keep it to scale, but whatever. By the Pythagorean theorem, we know this is true. A squared plus b squared equals c squared. 9 plus 16 equals 25. Okay, that works out. So here is the angle theta. Okay, so if I want to find the cosine of the angle theta, well, I know the cosine of the angle theta is the side adjacent to the angle theta divided by the hypotenuse. So cosine of theta is 3 over 5. If I want to find the sine of the angle theta, that'd be the opposite over the hypotenuse, 4 over 5. And if I want to find the tangent, that'd be the opposite over the adjacent. But let's say we weren't after those. Let's say instead we were looking to find the sine of double that angle, sine of 2 theta. Well, you can't just say, okay, the sine of theta is 4 over 5, opposite over hypotenuse. So then if I double the angle, that'll just be 8 over 5, right? No, sine, cosine, and tangent are not linear operations. If I double this, it's going to do more than just double the answer. Here, we're going to rely on the double angle formulas. 2 times the sine of theta times the cosine of theta. Right? Here, 2 is just a constant. I leave it alone. The sine of that theta will be the side opposite over the hypotenuse, 4 over 5. But then the cosine of theta will be the side adjacent over the hypotenuse, so 3 over 5. So if I double the angle, I don't just double the 4 over 5. I double the 4 over 5, and then I multiply by 3 over 5, which would give us, what? 4 times 2 is 8. 8 times 3 is 24. Over 5 times 5 is 25. So the sine of theta is 4 over 5, as we see here. But the sine of double theta isn't just double this, it's 24 over 25. Likewise, we could do the cosine or the tangent. In fact, you might want to give this a try. Take a moment now, pause the video to give yourself whatever time you need, and go ahead and find the cosine of double that angle. We already know the cosine of the angle is 3 over 5. Find cosine of double the angle. Once you're done, go ahead and unpause the video, and we can go through that together. All right, so let's go ahead and take a look now. We can take cosine of 2 theta and write it any of these 3 ways. It doesn't really matter. I think I'll just go with the first way. That's going to be cosine squared of the angle theta minus sine squared of the angle theta. Well, I already know cosine of theta. It's 3 over 5. Oh, but it should be cosine squared. Okay, so 3 over 5 squared. Minus, we're going to take sine of theta. Okay, well, that's going to be 4 over 5, but again, it needs to be squared, like that. And so now here, we're going to square both of these. That'll give us 9 over 25 minus 16 over 25. And then we can subtract those. 9 minus 16 will give us a negative 7 over 25. So if we have the cosine of 2 theta, so if we have the cosine of theta is equal to 3 over 5, the cosine of 2 theta is negative 7 over 25. It's not just a doubling of the answer, it is a little more involved than that. Note we can also use the double angle formulas not just for numerical computation, but also to confirm things about identities, to rewrite expressions in terms of other expressions. For example, we can verify the following identity. We're going to verify that 1 minus the cosine of double theta over the sine of double theta. And again, that theta can be an x or a w or anything else you like. 1 minus cosine of double your angle divided by sine of double your angle is equal to the tangent of your angle. Oh, there should be a theta. There we go. Keeping them all the same angle. All right. We can verify this by substituting in our double angle formulas. We can rewrite this. Notice the big difference between this and this is this has double angles, whereas this has a single angle. So we can rewrite these as a single angle using the double angle formulas. Here we can write this as 1 minus the cosine of 2 theta. I have a few options that I can use, but I notice that I'm dealing with a sine function, so I probably want to use this second one. 1 minus double the sine squared of theta. So cosine of 2 theta can be written as 1 minus 2 sine squared of theta. That's the second version of the double angle formula for cosine. That may not be the correct one to use, but it at least seems reasonable that I'd want to use that one. Now my denominator, sine of 2 theta, well, that can be written as 2 sine of theta cosine theta. All right. Some of these things can simplify. Right? Here, 1 minus 1, that subtracts away. And here you have minus a minus, which is a plus. So positive 2 sine squared of theta over 2 sine of theta cosine of theta. Double negative makes that a positive. Note that sine squared of theta is just saying sine of theta times another sine of theta. That's what squaring means. It means times itself. But when you write it that way, you note that 2 out of your 3 terms in numerator and denominator divide away. 2 over 2 is 1. Sine of theta over sine of theta is also 1. So in the end, you're left with 1 times 1 times sine of theta, which is sine of theta, over 1 times cosine of theta. And sine of theta over cosine of theta is equal to the tangent of theta, which does confirm our result. This does become the tangent of theta. Which confirms our identity. Okay, so our double angle formulas come in useful for numerical computation as well as for confirming identities and solving equations. There is another form of these double angle formulas which does come in handy. To begin, we're going to note this cosine of 2 theta is equal to either of these two. So we're going to start with those identities. So let's begin with cosine of 2 theta is equal to, and again, it's either of these two. It's either equal to 1 minus double the sine squared of theta, 1 minus double the sine squared of theta, or cosine of 2 theta is equal to is equal to double the cosine squared of theta minus 1. Okay? All right. From these two, we're going to derive the next set of our identities that we often use. Here, we're simply going to solve for sine of theta. I can go ahead and subtract 1 from both sides. So this will give me cosine of 2 theta minus 1 is equal to negative 2 sine squared of theta. Okay. I can now divide both sides by a negative 2. This will give me cosine of 2 theta minus 1 over 2 is equal to sine squared of theta. Oh, sorry, I'm dividing by a negative 2. And since I'm dividing by a negative, it'll switch my signs around. So this positive will now be a negative, and this negative would be a positive. Right? Negative over negative is a positive. So I'm going to write these as 1 minus cosine of 2 theta over 2. That's equal to sine squared of theta. This is called the power reduction formula. Sine squared of theta, you can lower the power by doubling the angle. Sine squared of theta is equal to 1 minus cosine of 2 theta over 2. This one becomes very useful in calculus, primarily because having a power of 2 in the sine function makes things in calculus difficult. We would rather have, in fact, any even power makes things difficult. So this is used now to compute a few numerical values and to confirm some identities and solve some equations, but eventually this is used because even powers of sine or cosine are difficult to work with for what we're going to want to be doing in later courses. By reducing the power, even though the angle gets bigger, having a smaller power makes things easier to work with. Likewise here, we can go ahead and add the 1 over this way. So this is 1 plus cosine of 2 theta. All right, that's a positive now on this side. That's equal to 2 times the cosine squared of theta. And now I can divide both sides by 2, and this will give me 1 plus the cosine of 2 theta over 2. And that's equal to the cosine squared of theta. So these are the power reduction formulas for sine and cosine. Notice they are almost exactly the same, the difference being that minus there is a plus over here. The power reduction formula for tangent is maybe a little anticlimactic. Note that the tangent squared of theta is equal to the sine squared of theta over the cosine squared of theta, which is equal to, well, the cosine squared of theta has its power reduction formula, 1 minus the cosine of 2 theta over 2. And then the cosine has its power reduction formula, 1 plus the cosine of 2 theta, and that's over 2. And now these 2's divide away, and there's your power reduction formula. So our 3 power reduction formulas are as follows. Sine squared of theta is equal to 1 minus the cosine of 2 theta over 2. The cosine squared of theta is almost exactly the same. That minus is a plus. 1 plus the cosine of 2 theta over 2. And the power reduction formula for the tangent function is basically this numerator over this numerator. 1 minus cosine of 2 theta over 1 plus the cosine of 2 theta. And these are the power reduction formulas. Here, as an example of how we can use the power reduction formulas, as I mentioned earlier, having even powers of sine or cosine is difficult in later courses. It's difficult to manage the kinds of problems that involve even powers of sine or cosine. So because of that, we often wish to reduce our powers until they're no longer power 2, 4, 6, or 8. We want odd powers. Those are easier to work with. So let's go ahead and write the expression as the linear combination of first degree terms. Meaning we want to make sure everything's power 1. We shouldn't have any sine, cosine, or tangent. Nothing should have power 2, 3, 4, 5. We want everything power 1. Okay? So let's go ahead and try sine to the 4th of theta. Okay? All right, well, sine to the 4th of theta is nothing more than sine squared of theta squared. Okay, so I can use the power reduction formula to write this looking like this. All right, so that'll be 1 minus the cosine of 2 theta over 2. But that is being squared. Okay, so things are better. That's not a power 4 anymore. I've got some smaller powered terms, but notice things are still being squared. Here, if we expand this out, we can see that. After all, if you square this, you're going to get 1 minus double the cosine of 2 theta plus cosine squared of 2 theta over 4. Like this. Note that this is a constant and this is power 1, but this is still power 2. It's still too big. So we're going to continue. We're going to use the power reduction formula again. Notice we used the power reduction formula for sine before. Now we're using the one for cosine. That's pretty common. Since they're related to each other, they often can switch back and forth. Here we're going to write this as, let me take this 4 and just factor as a 1/4, like that. So that's going to be 1/4, 1 minus double the cosine of 2 theta, plus, and now we're going to use the power reduction formula on cosine of 2 theta. Now notice, normally we take the power reduction formula on cosine squared or sine squared of theta. But here it's already 2 theta. So what does that mean for this one? Well, notice, whatever this angle is, this one doubles it. So whenever you use the power reduction formula, your angle will double. You say, well, that's already doubled. Well, then you're going to double it again. Double of a double. It's going to be power. That's going to have a coefficient of 4. So take cosine squared of 2 theta. That will be 1 plus cosine of 4 theta. You're going to take your angle, which was already doubled, and you're going to double that again. So that'll be 4 theta over 2. Basically, that theta becomes a 2 theta, and that theta becomes a 2 theta. So double 2 theta is 4 theta. Here, notice that that is common factor right here. I can factor out a 1/2. What I mean by that is here, instead of 1, I can write this as 2 over 2. Instead of 2, I can write this as 4 over 2. You say, well, yeah, I guess you could, but why would you want to do that? All right, why don't you just leave it as 1 and 2? Why do you write it as 2 over 2 and 4 over 2? Because now all terms have a common 1/2 factor. So I can factor out a 1/2. Now there's already a 1/4 on the outside, so 1/4 times 1/2, that's 1/8. And what's left on the inside? Well, once I factor out these denominators of 2, I'm left with a 2 minus 4 cosine of 2 theta plus 1 plus the cosine of 4 theta. Like that. Notice these are like terms. 2 plus 1 make 3. So here we can write this as 1/8 times 3 minus 4 cosine of 2 theta plus cosine of 4 theta. And now instead of having a fourth power of sine, now I have only first powers of cosine and a constant. For now, this seems like it's more complicated, right? This is just a single term, whereas this has 3 terms multiplied by a 1/8. But in later courses, we would rather have many terms of power 1 than to have one term with a bigger power. For many of our instances, this will be easier to handle. So this is an expression of this all in linear terms of sine and cosine. You may wish to try this now. Go ahead and give this a try. Go ahead and write sine squared of theta times cosine squared of theta. Go ahead and write that using only linear terms of sine and cosine. By the time you're done, you should only have cosines or sines or constants. Nothing to the second or third or fourth power. You're going to be using these power reduction formulas. So go ahead and give that a try. Pause the video. Give yourself as much time as you need. And once you're done, go ahead and unpause and we'll go through it together. All right, so let's take a look. Cosine squared of theta, that is the power reduction formula, 1 minus cosine of 2 theta over 2, times cosine squared of theta, that's going to be 1 plus the cosine of 2 theta over 2. And when we multiply those are going to give us, well, let's see, 1 times 1 is 1. 1 times cosine of 2 theta, but then that's minus cosine of 2 theta. So plus cosine of 2 theta minus cosine of 2 theta. Those cancel out. So really the only one we worry about is minus cosine of 2 theta times positive cosine of 2 theta. A negative times a positive is a negative. Cosine of 2 theta times itself is cosine squared of 2 theta. And then you multiply the denominators. 2 times 2 is 4. So now we're going to use the power reduction formula on this one. We've gone from power 4 down to power 2, but now we can reduce some more. Here, let me go ahead and write this as 1/4 times 1 minus cosine squared of 2 theta. All right, so now the cosine squared of 2 theta can be written as 1 plus cosine of 2 theta over 2. So this will be 1/4 times 1 minus 1 plus cosine of 2 theta over 2. Here, so I can join these together, I will write this 1 as 2 over 2. Like that. And so now the common factor of 2 in our denominator can be factored out. So 1/4 times the 1/2 we factored out, that's 1/8, times, well, we factor out the denominator, so that leaves us 2 minus 1. Here, this minus is going to have to distribute to both of these, right? After all, you're subtracting the whole thing, so the minus will distribute. So this gives us 2 minus 1 minus cosine of 2 theta. Oh, you know what? That is incorrect. I'm using the power reduction formula on cosine squared of 2 theta. Since that angle was already doubled, I need to double it again. So over here, this should be 4 theta. My apologies. Whenever you use the power reduction formula, you will double your angle. This one from angle theta to angle 2 theta. But once we use that power reduction formula again from here to here, the power 2 goes down to power 1, that angle 2 theta should double again to give me 4 theta. So here that should be 4 theta, not 2 theta. And so in the end, 2 minus 1 is 1. So this will give us 1/8 times 1 minus, that's a 1, minus cosine of 4 theta. And that is our result. Okay. Now, from the power reduction formulas, we can get the half angle formulas. One of the identities that we just established is that the sine squared of theta is equal to 1 minus the cosine of 2 theta over 2. Okay. All right, well, if I take the square root of both sides of this, this is going to give me the sine of theta is equal to plus or minus, remember when you take a square root, there's two possibilities, plus or minus the square root of 1 minus cosine of 2 theta over 2. But now let's say we took that theta and replaced it with something else. Let's say that theta got replaced by, say for example, x over 2. Right? You can replace things with whatever symbol you like. I can replace theta with w, with p, with x. Here I'm going to choose to replace that theta with x over 2. It's just a variable, it's just a notation, x over 2. Okay, well, if I have x over 2 times 2, well, those cancel out, leaves me just an x. So what I'm left with is the sine of x over 2 is equal to either plus or minus the square root of 1 minus the cosine of just my x. These 2's cancel out, leaving me just my x over 2. But notice what that means is if I have half of an angle, and before we had double of an angle, now if we have half of an angle, we can change it back to a regular angle by taking the square root of 1 minus cosine of that angle over 2. Likewise, we can do the same thing for cosine. Cosine squared of theta is equal to 1 plus the cosine of 2 theta over 2, which means that if I take the square root of both sides, I get the cosine of theta equals plus or minus the square root of 1 plus the cosine of 2 theta over 2. And if I replace that theta with an x over 2, that's cosine of x over 2 is equal to plus or minus the square root of 1 plus the cosine of, now that's going to be double x over 2. Well, the double and the divide by 2 cancel out, so I'm just left with an x over 2. These are very similar to each other, just like the power reduction formulas for sine and cosine were almost identical. The half angle formulas for sine and cosine are almost identical, the difference being that plus or that minus. And we saw that the tangent squared of the angle theta is equal to 1 minus cosine of 2 theta over 1 plus the cosine of 2 theta, which means that if I take the tangent of the angle theta, that's equal to plus or minus the square root of all of this stuff, 1 minus the cosine of 2 theta over 1 plus the cosine of 2 theta. And again, if I replace the thetas with with x over 2, this will give me tangent of x over 2 is equal to plus or minus the square root of 1 minus the cosine of x over 1 plus the cosine of x. Because again, the x over 2 will double, the 2's will cancel, leaving you just your x. So these are the so-called half angle formulas. For the sine of x over 2, that's plus or minus the square root of 1 minus the cosine of x over 2. Note plus or minus. That doesn't mean you're going to get two answers. We'll see an example of this in a moment. But what this means is you can have either the positive or the negative answer. Because remember, sine of an angle can either be positive or negative. It can go as high as positive 1 or as low as negative 1. So it's not that you'll get both answers. It's that you'll get the appropriate answer. You have the possibility of either a plus or a minus, and you have to choose which one is appropriate based off of the situation. Same thing for cosine and tangent. If you take cosine of x over 2, that's equal to plus or minus, and again, that doesn't mean both of them. It means whichever is appropriate. The square root of 1 plus the cosine of x over 2. And the tangent of x over 2 is equal to plus or minus the square root of 1 minus the cosine of x over 1 plus the cosine of x. Incidentally, there is another form for the half angle formula for tangent, and it is one that comes in useful from time to time because, well, it's slightly simpler looking than this and doesn't involve a square root. Recall at the beginning of this section, we verified this identity. 1 minus cosine of 2 theta over sine of 2 theta equals tangent of theta. Well, if I replace this theta with an x over 2, I can replace this theta with an x over 2 and this theta with an x over 2. The x over 2 And that 2, that would cancel, leaving me just an x. Same thing here, leave me just an x. So this is tangent of x over 2. Okay, that's what we have here, tangent of x over 2. That will equal to 1 minus cosine of x over sine of x. So that's equal to 1 minus the cosine of x over the sine of x. That's another and often very useful form of the half-angle formula for the tangent function. You can also jump through a few hoops, by which I mean you can do a little bit of algebra, and it turns out that you get a very similar one that looks like this. I believe in the assignments that you will have to prove this one. That's going to be the sine of x over 1 plus the cosine of x. So all of these are equivalent to each other, and you can either start from scratch, meaning starting from the tangent of x over 2 to get one of these, or it's probably a little simpler if we simply take one of these and rewrite until it looks like this. In your assignments, I believe this is one of your assignments to show that this is true, but for now, I'm going to take it for granted and say, well, we proved these two, and I'm going to leave it to you to prove that one. So these are the half-angle formulas for sine, cosine, and tangent. Of course, if you ever need the half-angle formulas or the double-angle formulas or really any formulas for secant, cosecant, or cotangent, always remember that's just the reciprocal of these. So the half-angle formula for the cotangent would just be the reciprocal of any of these. The half-angle formula for the cosine would be the reciprocal of any of these, for the secant. And the half-angle formula for the cosecant would be the reciprocal of this one. All right, so just remember, you don't need the other three separately. They're simply the reciprocals of these. So some examples of this. You're given a triangle. Here it measures 24 units, and that measures 7 units. And the question is to find the cosine of half of this angle right here. They call this the angle alpha. So cosine of alpha over 2. Okay. All right, so let's see. Using the half-angle formula, we're going to get that this is equal to the square root. Now you might say, well, wait a minute, plus or minus? How do I know which one? Well, let's see what situation we're in. Here, this is a right triangle. Oh, I forgot to draw that there. Here's a right triangle, and by the Pythagorean identity, a squared plus b squared is equal to c squared. Okay, well, let's see. 7 squared is 49. 7 squared is 49. 24 squared, 24, you can't see that, there we go. 24 squared is 576. And if you add those two together, you get 625. So add these two together, it's going to give you 625. Okay, well, 625 is itself a perfect square. It's the square of 25. So here, a squared plus b squared is going to equal to c squared, which means c must equal to 25. Okay? All right, so the cosine of the angle alpha would be the side adjacent over the hypotenuse, 24 over 25. All right, but think about what that would be on the unit circle. If you had an angle that gave you a cosine that was 24 over 25, that would have to be something that rests in one of these two quadrants, right? Because after all, cosine is positive either in the first quadrant or in the fourth quadrant. Now, what's the sign of this? Well, it's 7 over 24. Okay, well, that's still positive. So I would have a positive sine and a positive cosine. That puts me in the first quadrant. Okay, so whatever this angle is, it's over here in the first quadrant. Well, if I take that and cut it in half, so that I'm looking for the cosine of, instead of alpha, I'm looking for alpha over 2, well, notice that half of that is still in the first quadrant. Oh, so then its cosine should also be positive. So because this angle, because alpha over 2 is still in quadrant 1, that means that the cosine of alpha over 2 is going to be positive. Like that. Say, for example, your angle was down here in quadrant 4. Well, if you cut that in half, that's going to put you over here in quadrant number 2. And that would have a negative cosine. So that's why you have a plus or minus. It depends on what your starting angle is. When you cut it in half, that'll put you in some quadrant. Based off of that quadrant, you'll know that your cosine and your sine are going to be positive or negative. Right? So here, our angle alpha is in the first quadrant because everything about it is positive. And so if you cut that angle in half, it's still in the first quadrant. So here we definitely want the positive one. So plus the square root of cosine of alpha over 2. Well, that's going to be 1, we're using this formula right here, 1 plus cosine of alpha without cutting in half, 1 plus cosine of alpha divided by 2. 1 plus cosine of alpha over 2. We know the cosine of alpha because we can read it right off of this triangle. Cosine is adjacent over hypotenuse, 24 over 25. So this is the positive root of 1 plus 24 over 25 over 2. Here we can add these together. 1 is the same as 25 over 25. And adding those together would give us the square root of 25 over 25 plus 24 over 25 is 49 over 25 over 2. Here, dividing a fraction by a number, I just joined the two denominators together. So that'll give me the square root of 49 over 50. Here I can take the square root of 49, that's going to be 7. And I can take the square root of 50, that's 2 times 25. Well, I can take the square root of the 25 anyway to give me 5, and then the 2 would stay inside. So that'll be 7 over 5 root 2, like that. And finally, as we often do, we rationalize the expression. We don't generally want to have radicals in our denominator. So we're going to go ahead and take the square root of 2 multiplied on top and bottom, and that would give us root 2 times root 2, that's root 4, which is just the number 2, times that 5 would give us a 10 as a denominator. On the top, you have your 7 root 2 as your result. So if you have this triangle, you know the sine, the cosine, and the tangent based off of the ratio of these numbers. If you want to find the cosine of half of the angle, well, then you would use the power reduction formula to arrive at your result. There we go. Just like that. Let's take a look at another one of these. Maybe a little more general, since we're not actually given a triangle. We're simply given some values. All right. So let's see here. Let's consider the situation where we know the tangent of alpha is 8 over 15. So the tangent of alpha is equal to 8 over 15. And let's say that we know that the angle alpha is somewhere in the third quadrant, because the angle alpha will be bigger than 180 degrees, but it'll be less than 270 degrees. All right, so now the question is to go ahead and find all of the half angles. So we'll find sine of alpha over 2, cosine of alpha over 2, and the tangent of alpha over 2. So let's start with the first one here. All right, first of all, if I consider my unit circle an angle that is greater than 180 degrees, well, that's 180, and less than 270, that's 270 over here, that means that alpha falls somewhere in this third quadrant. Okay, so let's keep that in mind. Alpha is in quadrant number 3. Okay, now, the tangent of the angle theta is 8 over 15. So, if my angle theta looks like that, then that means that if I imagine I have my right triangle, and there's my angle alpha, the tangent of the angle alpha is the side opposite over the adjacent. Okay, so opposite of the angle alpha, that'll be 8. Right here, there's my angle. That's going to be 8, and the side adjacent will be 15. Like that. And I can find my third side using the Pythagorean theorem. I'm going to have a squared plus b squared. That's 64 plus, let's see, 15 squared is 225. Yeah. And then if I add 64 plus 225, I end up with 289. Like that. Oh, but 289 is a perfect square. After all, it's 17 times 17. So that means that if I have a triangle that has a tangent of 8 over 15, opposite is 8, adjacent is 15, the hypotenuse must be 17. That way, a squared plus b squared can equal to c squared. Okay? So I have that ratio of, I have that arrangement of a right triangle. Okay? And remember, I'm in the third quadrant. All right, so now let's find the sine of the angle alpha, sine of the angle alpha over 2. Sine of alpha over 2 is equal to plus or minus the square root of 1 minus cosine of alpha over 2, like this. Okay, well, first of all, plus or minus, which one? Okay, well, this is between 180 and 270. Okay, well, if I cut it in half, well, half of 180 is 90. And half of 270, that will be 135. So if the angle alpha is between 180 and 270, that means the angle alpha over 2 would be between 90 and 135. So it would be over here in quadrant number 2. So in quadrant number 2, sine is positive, cosine is negative, and tangent is negative. So right here, the location where alpha over 2 lands you, in this case quadrant number 2, that informs which of the radicals I want. Since alpha over 2 is in quadrant number 2, that will inform whether we want a positive or a negative for each one. Alpha over 2 is in quadrant number 2. All right, so here in quadrant number 2, the sine of an angle will always be positive. Okay, so we don't want the negative one. Okay, alpha, well, that's this angle over here, before we cut it in half. Okay, well, what's the sine of, the cosine of that alpha? Well, cosine is adjacent, which is 15, over hypotenuse, and that's 17. So that'll be the positive square root of 1 minus, again, cosine is 15 adjacent over 17 hypotenuse, and that's divided by 2. Here we can combine those, 17 over 17 minus 15 over 17, that's 2 over 17, and that's divided by 2. And so these 2's can divide away, and you're left with simply the square root of 1. After all, 2 over 2 is 1. This is going to leave you the positive square root of 1 over 17. Here, I can take the square root of the top, separately the square root of the bottom. I can do that with any fraction. And finally, let me rationalize this. And that'll give me root 17 times root 17, which is just 17. And the numerator is going to be 1 times root 17, which is just root 17. Note that that is a positive value because, again, your alpha over 2, the angle that you're looking for, the sine of the angle that you're looking for, rests in quadrant number 2, which means it must be a positive sign. Oh, actually, my apologies. I made a sign error here. So let's see. Yeah, I've made a sign error here. So that's a positive. 1 minus cosine of alpha. Okay, that's fine. But notice, alpha was over here in quadrant number 3, the original angle, right, between 180 and 270. So that means that the cosine of the angle alpha would be a negative 15 over 17. These give me the ratio. These give me the numbers, right, adjacent over hypotenuse. But since it's in quadrant 3, that 15 over 17 would be a negative. So this is minus a minus. Right? That negative comes from the formula. This negative comes from the fact that alpha is in quadrant number 3, so the cosine of alpha is a negative. So minus a minus is plus. Okay, so that changes things a little bit. 17 over 17 plus 15 over 17. Okay, so that would be what, 32 over 17? So 32 over 17. Oh, and just by a nice happy coincidence, I can still cancel things out. So here 32 over 2, that's the same as 16. Right? So 32 divided by 2 is 16 over 17. Now I can take the square root of that 16, which is a 4, over the square root of 17. And now I can rationalize this. Square root of 17 times square root of 17 is just 17. 4 times the square root of 17, that's my answer. And again, it's positive because even though this is in quadrant number 3, the cosine of the angle that I'm looking for is in quadrant number 2. So this one's our result. My apologies, I had a sign error. This should be minus of a minus, which is actually plus. So that is the sine of alpha over 2. Go ahead and try the other two. Go ahead and pause the video and finish off the problem. Go ahead and find the cosine of alpha over 2 and the tangent of alpha over 2. And again, don't forget that it has to rest in the correct quadrant. Pause the video for whatever amount of time you need. And once you're done, go ahead and unpause and we'll finish it together. All right, let's take a look at the cosine of alpha over 2. The cosine of alpha over 2 is going to be, again, plus or minus the square root of 1 plus the cosine of alpha over 2. Okay. All right, well, plus or minus. The cosine of alpha over 2. Since alpha over 2 rests in quadrant number 2, its sine is positive and its cosine is negative. So here, because you're in quadrant number 2, you're going to be using the negative radical. So it's going to be a negative answer. All right, so that's going to be negative the square root of, well, let's see, 1 plus the cosine of alpha. Okay, well, let's see. We already know that the cosine of alpha is negative 15 over 17. But now instead of subtracting that number, now you're adding that number. So it's very similar to the previous computation, except that instead of 1 minus that, it's 1 plus that. Over 2. Notice, once again, cosine of alpha is negative because alpha rests in quadrant number 3. Okay, well now that's going to be 1 minus 15 over 17, right? Plus a negative is minus. That's 17 over 17 minus 15 over 17. That's 2 over 17. So that's going to give us the negative square root of 2 over 17 over 2. And then the 2's divide away. 2 over 2 is 1. So this gives us the negative square root of 1 over 17. Okay, 2 over 2 is 1. We can take the square root of the top. That's just negative 1, right? The negative and the 1 over root 17. And finally, we rationalize our results, multiplying top and bottom by the radical of 17, which gives us negative root 17 over 17. And cosine of alpha over 2. Finally, we want the tangent of alpha over 2, and we can do one of two things. We can either use the half-angle formula for the tangent, or we realize that, hey, tangent of alpha over 2 is sine of alpha over 2 over cosine of alpha over 2, which is probably a lot simpler. Tangent of alpha over 2 is equal to sine of alpha over 2 over cosine of alpha over 2. But we know both of those numbers. Right? Sine of alpha over 2, that's 4 root 17 over 17. And then over cosine of alpha over alpha over 2, that's going to be negative root 17 over 17. Here the root 17's divide away, the 17's divide away, and you're left with 4 over negative 1. Since everything divides away, that's just 1 right there. Well, it's got a negative in front. Okay, negative 1. So that's 4 divided by negative 1, which is negative 4. So we get that the tangent of alpha over 2 is negative 4, which alpha over 2 is in quadrant number 2, which that checks out. Sine is positive, cosine and tangent are both negative. And those are our results. Okay, for our last problem here, for our last set of examples, let's go ahead and consider an identity. Let's verify the following identity. Oftentimes, we only have a few identities in mind, after all of these years of both doing and teaching math, the trigonometric identities that I have memorized, that I've used over and over again in order to memorize them, have been the double angle, the half angle, the power reduction, and the sum and difference formulas. Basically the ones that you see in this section. They're the ones that are useful enough to remember. Most other identities are not useful enough to remember in their own right. Rather, we take a few basic ones and can confirm those as we need to. So here we're going to confirm one that is not particularly useful very often, but which is nonetheless true and which can be useful in its own appropriate situation. So here the statement is that the square of the sine of theta over 2 is equal to the secant of theta minus 1 over double the secant of theta. Okay. When we verify an identity, we begin with the most complicated looking side. Now, sometimes that's a matter of opinion. Here, I would say this is the most complicated looking side because it's got a square and a half angle. All right, that's just got single angles, no problem. Other people might say, well, no, it's got a quotient and there are secants. Yeah, this looks easy because it's just got a sine. Okay, so it's sort of a matter of opinion. But I would suggest we do this one, starting from this side, mostly because, well, that's kind of what we're looking at right now. We're looking at half angle formulas, and it's a useful thing to be able to use those, not just computationally, but also to prove or to establish an identity. So go ahead and give this one a try as well. You can start from either side. However, I suggest you would start from this side. In the end, you may get a different proof than I do. You may get a different verification, but as long as you can, following all of the identities that we've had, half angle, double angle, power reduction, or anything else, if you can transform this into this, or vice versa, that is sufficient to verify the identity. So go ahead and pause the video, give yourself the time you need, and once you're done, go ahead and unpause, and we'll go through that together. All right, so here I actually have two different ways that I might approach this. I have a power of sine, which means I could use the power reduction formula to bring this power down. Or I see a half angle, I could use the half angle formula to bring this angle back to a regular theta. Remember that the half angle formula and the power reduction formula are just two different points of view of the same formula. So here if you say, no, why are you going to choose one over the other? I'm really not. They are the same. Remember, we derive the half angle formulas by starting with the power reduction formulas and then solving for the sine of theta, right? Replacing sine of theta with x over 2. So the power reduction formulas give you the half angle formulas. So here, I'm not really choosing one over the other. They are the same. Here, I'm going to state it from the point of view of the half angle formula. If you use the power reduction formula, it will give you the exact same result. Note here that if you take the sine of an angle over 2, that's going to equal to plus or minus the square root of 1 minus cosine of the angle without being cut in half over 2. All right, well now notice that that's being squared. Okay, so that's sine squared of theta over 2. That's equal to this thing squared. Right? Because after all, that is another way of writing sine of theta over 2. But now when I square this, it doesn't matter if it's plus or minus. When I square things, they all end up positive. So I don't have to worry about a plus or minus anymore. It's all positive. Taking the square of the square root will leave me just what's inside, 1 minus the cosine of the angle theta over 2. I notice that I have a 2 in my denominator, but I don't have a secant of theta, which is one thing that I'm hoping to end up with. So let me do that. Let me multiply by secant of theta, but whatever I do on the bottom, I have to do on top. So here this will be 1 times secant of theta, which is secant of theta, minus cosine of theta times secant of theta. Well, yeah, but isn't secant of theta the reciprocal of cosine? Isn't that the same as saying 1 over cosine of theta? So 1 times secant of theta is secant of theta minus cosine of theta times secant of theta. And I'm going to write secant of theta this way because now these two divide out. The denominator is now double the secant of theta. And once these divide away, we're simply left with 1 as a constant. So this now gives us that sine squared of theta over 2 is equal to secant of theta minus 1 over double the secant of theta. which is what we were trying to confirm. You may not have done exactly the same steps. You may have started with a power reduction formula instead. Or you may have started from this and tried to work backwards. It doesn't actually matter as long as every step in your process is equal to every other step, meaning as long as you used a valid identity, it doesn't matter what path you take. As long as you can connect one to the other, that is sufficient to confirm our results. Note that in problems like this, there is no single final answer. Here, every step along the way to go from one side of your equation to the other side, every single step is necessary. Here, this is not the final step. All of it is. So normally I put a box around the final answer. In this case, there is no final answer. The entire thing is the result. All of it. And that brings us to the end of this. This is the end of our section. We have looked at three kinds of identities, the power reduction formulas, the half-angle formulas, and the double-angle formulas. Note that they are all related, and one can be derived from all of the others. If anybody has any questions, comments, or problems, please let me know, and I hope everyone has a nice day.